Today, I'm going to try out the Tianshou Reinforcement Learning library. Some of the selling points of this library is high performance, modular framework, user-friendly. What does modular framework mean? Let's hop over to their documentation. The four components that make up this library is the trainer, collector, data buffer, and policy. Let me hop down here. Let's start with the collector. The collector is the one that interacts with your environment and collects the action, reward, and the states. Basically collecting the experience and adding it to a buffer. The policy interacts with the model. The model is the neural network to be trained. The policy is the learning agent. It reads experiences from the buffer and updates the model. The trainer is the high-level component that orchestrates this whole thing. When they say modular, it means that you can swap out, for example, the buffer, switch it out to prioritize replay buffer or hindsight experience buffer. Policy, of course, you can change it into any one of these reinforcement learning algorithms. And then the collector, I think you can collect experience synchronously or asynchronously. So that is what is meant by modular. You can swap things out, kind of like Lego pieces. Now, in terms of user friendliness, having tried this out already, I would say this is more of a intermediate level library. For example, if you want to use DQN, you do have to have a pretty decent idea of how DQN works. Otherwise, it's going to be really hard to use this library. And once we get into the code, you'll see why. Okay, let's get it installed. Let me bring up my Anaconda prompt. And I'm going to create a new Conda environment. Conda create, give it a name, and just call it Tianshou ENV. Use the latest version of Python. Okay, it's done. Let me activate the environment. Copy this and activate the environment. And then go down to the installation. Pip install Tianshou. Okay, it's done. Okay, here's what we're going to do today. Let me hop up to the top of their GitHub page, click on examples. The one we're going to try today is the DQN example. There are two versions of it. This one is named HL as in high level. This is their highest level of abstraction. Look at this. This variable is pointing to a whole chain of things. I think it's going to be really hard to debug if anything goes wrong. And it's really hard to understand what's happening at this level. So we're going to use this one instead. This one is much more modular. So what I'm going to do is I'm going to copy the code from here into my VS Code. And we're going to see what is actually happening. Okay, let me go over to VS Code. I just have it pointing to an empty folder. Let me create a new file. We'll try the DQN module and we'll create a Jupyter notebook. Over here, I'm going to select the environment that we just created. It is called Tianshou ENV. Let me hide this and then let me do side by side with that example code. Let's bring in the imports. Run it. First time you do Jupyter in VS Code, and it's gonna ask you to install some Jupyter modules to support it. Okay, the code is running, and I'll explain what these things are when we actually start calling them. Let me keep going down. Create a new code block. So we're gonna try it on good old Cartpole. These are all the hyperparameters. You got the learning rate, and I will explain them as we use them. Just run it. Keep going down. Okay, this is the logger. Let me bring up another diagram. You can see the trainer, policy, collector, and buffer that was in the more high-level diagram. In this code, we're going to build out all these components. First one that we have here is the logger. The logger is over here. It's basically a helper class that allows all these components to log their information to. The logs are going to be saved into the folder it's going to pop up here under log/DQN. The logs can be viewed by TensorBoard, and you can bring up TensorBoard inside VS Code, but I like to bring it up in a browser, so I don't want to use the integrated TensorBoard. Now, let's go to the next one. Now we're creating two sets of environments. The first set is for training. The second set is for testing. Let me hop over to this diagram. So what the code is doing is this part here. We're creating a vector or a list of environments. We want to be able to train on multiple instances of the same environment, ideally in parallel, to speed up training. So there's actually two sets of these, two sets of vectors, one for training, one for testing. What is happening here, train num and test num are defined up here. In the demo, they have 10 training environments and 100 for testing. In case you're not familiar with Lambda, the way we write this out is it's a for loop for 0 to the number of training environments and calling gym.make. Task is up here. Task is Cartpole. As we create the instances, we would be probably calling .add or something like this. So this one line is basically doing this. Why is this called dummy vector environment? When we do training or testing using the dummy vector environment, it doesn't do real parallelization. It still operates on one environment at a time. The purpose of this really is just easier for debugging, since you can trace through one environment at a time. Once you're done with debugging and you know the code works, you would switch it out to this one, subprocess vector environment. We replace dummy with the subprocess vector environment, and that one offers real parallelization. Again, depending on how many processors you have, how many cores you have, and how much RAM you have, you might want to change this number to higher or lower. Okay, let me get rid of this and then we'll run it. Next, looks like we're creating the model. It's this piece that the policy is interacting with, which in this diagram is the PyTorch module. So we're creating this one now. And I'll just put the import up here as well. Run it again. Copy this. Okay, why are we making the environment again? Here we're doing a search statement to make sure the action space is discrete. Cartpole does have a discrete action space. We're using this space info class. Space info is used to get the observation shape and the action shape. We're passing that into the network. Remember, in DQN, the network input is the state. So passing the shape of the state here. The output are the nodes for the actions, or the Q values associated or estimated for the actions. So we got the input shape here, the output of the network is the action, and then you got the hidden layers here. They're doing 3 hidden layers of 128 nodes each, which is really big for Cartpole, but I'll leave it for now. And then declaring the atom optimizer, passing in the network's weights and biases into the optimizer, and also passing in the learning rate, which was defined up here. Okay, let's do this. Next, we're moving on to the policy. So we have the environment, we have the network, and the policy is going to take in the network and also act as the agent. In the policy, we need to give it the network. The optimizer we just declared, gamma, is declared up here. The action space, we can get that from env.actionSpace. And then both end step estimation and target frequency also declare up here as 3 and 320. This is where I mentioned before that you have to be pretty familiar with DQN in order to use this library. You have to know that when you declare a target frequency, you're using both a policy network and a target network. Also, there's end step estimation. So what even is that? Looks like this is another technique within temporal differencing, something I haven't looked at before. I'll leave it the way it is. Declare the policy Next, we have the two collectors. So the agent is done. We're declaring the collector component now. We're declaring two collectors, one to collect experiences for training, one to collect experience for testing. We need to pass it the policy, the set of training environments, the set of testing environments, and also for training, we need to give it the buffer. That is this one right here. This is the list of buffer that correspond to the environments. The experiences for environment 1 goes into the first buffer. Second environment's experience goes into the second buffer, and so on. So we had 10 training environments and a buffer of 20,000 total. 20,000 divided by 10. That means each buffer is going to hold 2,000 sets of experiences. The test collector doesn't collect anything into the replay buffer. It's really just to collect the experiences and use it immediately for testing. So that's why this one doesn't have the vector replay buffer. Now, exploration noise. Looking at the documentation, base policy, it's supposed to add noise to exploration. You can see a note from here that it actually doesn't do anything. So we'll ignore it for now. There's an error here that says collector is not subscriptable. It seems like there's a bug here. If I get rid of these, this code works. Next, we'll define the stop function. This is a callback function. During training, we're going to pass this to the trainer in just a second. During training, the trainer will periodically call the stop function and pass in the current mean reward. It gets the mean reward from the test collector. Here you can write custom code to stop training when a certain reward threshold has been met. In Cartpole, I think it's defined to be either 200 or 500. Here, when the mean rewards reach the threshold, we can return true and stop the training. So this is how we can automatically stop training. Define the function. All right, we're almost done. We have the policy, we have our collector, and now we're declaring the trainer. There is a lot of parameters here. This is only a subset of it. Again, why I call this more of an intermediate level library. Here you need to know that DQN is a offline policy. We're passing in the policy, training collector, test collector. The next bunch of parameters are defined up here in the hyperparameters. Batch size is the mini batch size. So every time we're retrieving 64 samples from the replay memory. I think it's easier once I run it. I'll explain what these parameters are again. So let me jump down to here. You've seen the logger from up top. We're just passing it in. You saw the stop function. And now you can also pass in two hooks for training and testing. The training function, again, they're using lambda here. The function receives two pieces of information, what epoch they're in and what environment step they're in. Inside the function, they're calling policy. This policy dot set epsilon. Epsilon train was defined up here. So the idea is to lower epsilon, but in this sample code, they're just repeatedly sending in the same epsilon. They're not decaying it. I guess for Cartpole, because it's so simple, even with a static epsilon, the training still works. But in a little bit, I'm going to add a function to decay epsilon just to show you how that works. Also in the test function, they're also setting a epsilon. I'm not sure why. For testing, we should probably use exactly what the policy has learned so far. So putting in epsilon here at least doesn't make sense to me. But let's run the training as is. And I'll explain some more on these parameters. So now on the left side, we got the whole thing. We got everything in the diagram implemented. I'm going to maximize VS Code. You can see here, this is going to stop at epoch 10, which was what the epoch hyperparameter was set to. And then within each epoch, it's doing 10,000 steps. 10,000 is defined here. step per epoch. Okay, training finished in about a minute. We can see at the end that it's capable of doing 200 actions before the pole falls down. Now going back to the epoch, 10 epoch times 10,000 steps each means it's a total of 10 times 10,000 or 100,000 steps. Training will either end at 100,000 steps or it will stop when the stop function returns true. Now what is one step? One step is actually one step of one environment. So that's a very important distinction. It's not one step through all the n environments. Since we declared 10 environments, one pass of going through all this, it actually takes 10 steps to iterate through all 10 environments. We can see here that it says it did 10,001 iterations. So 10,000 steps. I'm not sure where there's an extra one yet, but this should correspond to the number of steps. Here it took 7 seconds to do one epoch at a speed of about 1300 iterations per second. You can use this to gauge how fast the environment is running. So this is a number that you can try to optimize, maybe by decreasing the size of the model. The step per collect here, let's see what it's defined at. It's defined to be 10. It's defined as 10 because there are 10 training environments. So each time we collect one step from each environment. However, even knowing that math, I'm not sure why we would increase or decrease this number. There isn't enough explanation in the documentation or enough examples to show me why I need to change this number. So for now, let's leave it the way it is. Episodes per test is defined as 100. What it's going to do is, after one epoch of training, it's going to do testing with 100 episodes. It's going to take the average of that 100 episodes. Here we can see that the average is 223 with a variance of plus minus 59. Over here, it shows you what the best reward is so far, and it was found in, of course, epoch 1. Now, if we go down a little bit, we can see that in epoch 2, there's a new best reward, but then it hasn't changed. So from epoch 2 to 10, looks like the best reward was found in epoch number 2. Back to steps per collect, that actually affects this stat over here. There is another parameter here called episode per collect, which affects this log item right here. I think episode per collect probably has more use if you want to ensure a minimum number of episodes collected within an epoch. Here we can see that during training, this is the average reward. Batch size, you saw from up top that it was set for 64, and it's going to sample the buffer for 64 samples each time. Now update per step. This affects the gradient step here. You can see that it's set to 1 divided by steps per collect, which was set to 10. So 1 over 10 is 0.1. 0.1 times 10,000 steps is equal to 1,000 gradient steps. So what this is saying is after each environment takes one step, do one training step. Now it's nice to be able to set all these customizations, but I think all the math behind it, it's a bit too complicated. Okay, so let's check the log here. You can see after running at one time, it created a log here. We can use TensorBoard to take a look at this log. I'll go up to terminal, click on new terminal. Notice that on the left side here, it doesn't show us the conda environment. So if I try to type TensorBoard, it's not going to work. So in VS Code, if I hit Ctrl-Shift-P to bring up this command prompt here, you notice the first one is select interpreter. If you don't see it, just type Python. I'm going to select the Tianshou environment. So selecting this environment and selecting the environment in Jupyter, it's two separate actions. Now let me kill the terminals and open it again. Now my terminal is tied to my conda environment. Now it should see TensorBoard. I'll give it the name of the log folder. says TensorBoard has been started. I'll hold Control and follow this link. And here is TensorBoard. You can see a bunch of nice graphs. You can see the reward, the best reward graph. It jumped from 220 to 300. Best reward, standard deviation. Okay, so there's a lot of stats that you can take a look at. This doesn't have epsilon decay, but we can add it easily. Let's go back to VS Code. I'm going to insert a code block here and paste this in. I'm going to define a train function that I can pass into here. Remember that the function signature is epoch and environment steps. Epoch and environment steps. I'll just replace this with the train function up here. And this I'm just implementing epsilon greedy, starting epsilon at 1 and then ending it at 0.05. So this is just some formula to do linear decay. After each environment takes a step, we'll decrease epsilon by a little bit. So you can mess with this function yourself. I'm not gonna go into it. So after calculating the new epsilon, we'll call the set epsilon function on the policy to decrease epsilon. And then to get it into TensorBoard, we use the logger that was defined up top, called the right function. We have the environment step as the x-axis, and then epsilon as the y-axis. Now if I run training again, I'm going to get 2 logs, and then on TensorBoard it's going to have multiple graphs on there, and it's going to look pretty confusing. So let me delete the log and then clear all the outputs. I'll run everything from above again. And then I'll do the training. Let me also restart TensorBoard so it forgets about the previous log. Another way to do this is probably to make this more dynamic and change the folder name each time we do a new training. That way we're not graphing multiple trainings on the same graph. And the result isn't any better than before, but we're just adding it just to show you. So now training is done. We can go back to TensorBoard. Let's see where epsilon is. So what I did was click on these headers to minimize it. It's the training card that we added the epsilon to. Since we added it to the end, scroll all the way down, you can see there's multiple pages. Click on next. And you can see what we added here. So you can see it starts with 1 and it decreases over time all the way to at 90,000. That's where I set it to stop decaying, and then the rest of it stays at 0.05. Okay, so this is how you can add something to TensorBoard and visualize it. Now finally, after training, we want to see our results, right? Let's add another block. So going back to the sample code, I found that this actually didn't really visualize the environment, and I modified this a little bit. So let me copy my version in. Okay, I'm creating a new environment separate from what was done up top. Make sure that we pass human to render mode so that we can see the test render onto the screen. We need to pass that to the collector, creating a new collector, and passing it the policy that was trained up top. And then we call the collect function. I'll just run it for 1 episode, rendering it at 30 frames per second. And then we have to pass in reset before collect equal to true so that it automatically resets the environment before running this code. Just saving the results here and printing it out, and then closing the environment. Now let's try it. There's an error here, it says no module named Pygame. So we're gonna have to install Pygame. Let me do a new terminal. And I'll just do pip install Pygame. Clear this message. Okay, Pygame is installed. Let me do this again. Oh, it popped up. Okay. Let me put it side by side. I'm gonna run it one more time. All right. So our best results are around 100 actions. The best it can get was 382, and that's why the Cartpole fell pretty fast. Of course, we can increase the epoch, and eventually the Cartpole is going to stay up forever, but I'll leave that up to you. If you enjoyed this type of video, make sure you thumbs up and drop me a comment. I'll catch you next time.